All right, let's dive into one of the wildest, most fascinating ideas in all of modern technology. We're going to break down how it's actually possible to prove you know a secret without giving away even a single hint of what that secret is.
But let's back up for a second and start with a question that's probably more fundamental than we realize. Every single day, you log into things, you send messages, you open apps. You're putting your faith in code you've never seen, written by people you've never met. But can you be absolutely sure that software is doing what it's supposed to and only what it's supposed to? This isn't just some abstract worry. It's a classic, deep-rooted problem in computer science. It's the kind of problem that can create the perfect, completely invisible backdoor. Ken Thompson, and if you don't know the name, he's basically one of the godfathers of the Unix operating system. He nailed this idea perfectly. This quote right here gets to the absolute core of what's called the trusting trust problem. The real issue isn't just the code you can see, it's the tools that were used to build that code in the first place. So check out this thought experiment he came up with. It's both brilliant and, honestly, a little terrifying. A programmer writes a perfect, secure logging program. No bugs, no flaws. But to turn that source code into a program you can actually run, they use a compiler that's been secretly tampered with. That compiler injects a hidden backdoor. But here's the real kicker. It also modifies the compiler's own source code so that the next time the compiler is built, it will teach itself how to do the exact same thing again. It's a self-replicating backdoor that's completely invisible in any source code you look at. A total ghost in the machine. So, if we can't even trust the basic tools we use to build software, how can we possibly verify anything? Well, this problem leads us to a solution that sounds completely impossible. A way to prove something is true by revealing, well, absolutely nothing at all. And that brings us to the formal definition of a zero-knowledge proof, or ZKP. It's a way for a prover to convince a verifier that they know something without revealing any information other than the fact that they know it. It's kind of like proving you know the punchline to a really good joke without ever actually telling the joke. And I'm sure your first reaction to that is probably, hold on, what? How on earth could that actually work? And if you are thinking that, you're in the right place. It feels like some kind of magic trick, but it's really just incredibly clever math. So, to strip away the magic and show you the logic underneath, we're going to use a really famous analogy. It breaks down exactly how this impossible-sounding idea actually works. Okay, so imagine a cave that's shaped like a ring. It's got two paths, a left one and a right one, but at the very back, they're connected by a magic door. And this door will only open if you know the secret password. This is the stage for our proof. Here's how the game is played. We have Peggy, our prover, who claims she knows the password. She goes into the cave and picks a path. Left or right, doesn't matter. A little while later, our verifier, Victor, shows up. He can't see which path she took. He just randomly yells out, "Come out the left path," or "Come out the right path." Now, if Peggy happens to be on that side already, no problem, she just walks out. But if she's on the other side, she has to use the secret password, open that magic door, and come out the path Victor called. Now, this is where it gets really cool. If Peggy is faking it, if she doesn't know the password, she's just guessing which path Victor will call out. She's got a 50-50 shot of being on the right side by pure luck. But what happens if they do it again, and again, and again? If they run this little test just 20 times, the odds of her guessing correctly every single time by chance are less than 1 in a million. Victor never learns the password. He never even sees the door, but he can become almost completely certain that she must know it. That is a zero-knowledge proof. So obviously, this is more than just a clever puzzle about a cave. This simple idea is the bedrock for a massive change in how we think about security and privacy online. Just think about how you log into a website right now. You type your password and it, or at least a version of it, gets sent to a server somewhere. If that server gets hacked, your login details are at risk. Now, imagine a world with ZKPs. You don't send your password, you just send a tiny mathematical proof that you know the password. The password itself never ever leaves your computer. So if a hacker breaks into that server, there's literally nothing valuable for them to steal. And this goes way beyond just passwords. ZKPs are already powering private transactions on blockchains. They could allow us to verify an election was counted fairly without revealing how anyone voted. Or you could prove you're old enough to buy a drink without showing an ID that has your name, your address, your exact birthday, all that extra information. The most important thing to get here is that this tech lets us fundamentally change the rules about how we handle private data online. But as you'd expect with any groundbreaking technology, it's not one size fits all. Different methods are popping up, and each one comes with its own incredible strengths and some really interesting trade-offs. This is where things get really cutting edge. The two big families of ZKPs that everyone's talking about are called ZK-SNARKs and ZK-STARKs. They're both trying to do the same thing, but the way they do it is really different. And those differences have huge implications for security and for trust. Now, to get the difference, you first have to understand a potential risk. A lot of the early ZK-SNARKs need something called a trusted setup. It's this one-time event where secret random numbers are used to kickstart the whole system. The problem is, if those secret numbers aren't destroyed perfectly and completely afterwards, anybody who gets their hands on them could create fake proofs that could counterfeit trust itself. This leftover secret data has a perfectly dramatic name: toxic waste. And this table really lays out the big trade-offs. SNARKs often need that trusted setup, which means you have to worry about that toxic waste. STARKs, on the other hand, are transparent, no secret setup needed, which a lot of people see as a huge win for security. Plus, STARKs are built using math that we think will be safe even from future quantum computers, which is a massive deal. So what's the catch? Well, for now, SNARK proofs are generally much smaller and a bit faster, which makes them more efficient. So it's this fascinating choice between today's performance versus tomorrow's security and trust. And that kind of leaves us with this final big idea. We've just walked through a technology that completely flips the script on how we think about data and privacy and proof. It shifts us from a world where we say, trust me, here's my data, to one where we can say, you don't need to trust me, here's a mathematical proof. So the real question isn't just about how this stuff works, but what incredible new things we're going to build in a world where we can finally verify without revealing.